critical numbers are where f prime of x equals 0. So you're gonna take a derivative of this function. That's why you learned all those derivative rules. 3 times 12, that's 36x squared, because you subtract 1 from the exponent. 2 times negative 27, so minus 54x. And then whenever it's a number times x, it just becomes the number. So that's 18. You're going to factor out an 18, so that's 2x squared minus 3x minus 2. And then you would factor this, and you get, let's see here, minus 2 plus 1. And you set these equal to 0. So that's 2x plus 1 equal to 0. And x minus 2 equal to 0. So x equals minus 1/2, x equals 2. So those are your critical points. And I think they want you to separate them in a list here. Yeah, so you would just write minus 1/2 comma 2.
Okay.
Now, we could do this kind of the traditional way, but probably just to make this, you know, as straightforward as possible, I'm actually going to graph the function, and then I'm going to snip in a graph of it, and we'll do this another way, just to save a little bit of time here. But I'm graphing it right now, and I will snip in the graph once I get that up. Oops. I got to get the right window. That's the biggest problem here. So let me grab a snip here. Okay. Okay, so the graph is coming in here shortly. Really helps when they give you the graph. So this is the graph of the original function. Okay, so we want to know where it's increasing in part B. So we know it's increasing when you're looking at the original function when it's going up and to the right, and you can see both of these x values correspond to the ones that we just calculated by hand. So if it's going up and to the right like it is here on the black, and then here again in the black, you can see that and those, we're looking at the x values again for that. So it's minus infinity to minus 1/2, all of these x values, comma 2 comma infinity. And then decreasing is the other interval. So it would be from minus 1/2 to 2. So the graph really helps. If we had to do this by hand, it's slightly more difficult, but it's definitely doable.
Okay.
But that is, I think that's everything for that's A, B, and C.
Okay. I gotcha.
So for whatever reason, 4 and 5 did not come in as attachments. Same with actually 7 and 8. I'll start putting those in the chat. Yeah, they're just showing us little thumbnails. There's gonna be more here. 14. I apologize. I didn't scan the email before the lesson. I just said, oh, they're there. There's pictures. Okay. Let me try it another way and see if they come in. Oh no, you know what? That's interesting. Okay, 4, I do have them. I just had to do it a different way, and now,
oh geez,
now they're there.
Great.
Love Google. Sometimes
I will blame Google that time, because I really made sure that they were all good.
Yeah. Looks like it's all right. So suppose that the total cost is given by this function here. So they don't want the critical numbers this time. You would find them by taking the derivative and set it equal to 0. And so some instructors are completely okay if you just graph it and do it the way that we've been talking. The only time it doesn't work is when the critical numbers are at sort of values that aren't very nice. So we'll see if that's the case here. So I'm just graphing it in this other window, and I will snip in the this here. Yeah. So actually, this is an interesting question here for us. So it's a cubic. This is a cubic, and cubics have at most 2 turning points. Like the type of cubic you're used to is where turns and then turns, but they don't have to have a turning point either. They can actually just go, kind of nice and smoothly up forever. So when it's, let's look at where it's increasing first. It's increasing everywhere. It's always going up and to the right.
Okay.
So for part B, it's all real numbers. It's from -infinity to infinity. It is never decreasing. So I believe it's that second option when you're entering it, where you're basically, oh yeah, the function is never decreasing.
Okay.
And that does happen. So there's actually many functions that are always increasing or always decreasing. That is possible.
So for part A, we have the answer of B, and then
Yes.
for B, we have -infinity to infinity.
Yes.
Okay.
Yes.
Gotcha.
Okay. All right. So I going on to 5. I do have it. Okay, it says find the values of all relative extrema for the function with the graph below. So extrema are kind of the following here. They are what are called local mins, local maxes, absolute mins, and absolute maxes. And this problem doesn't illustrate this very well, but this point right down here is a minimum. I mean, I think it illustrates that it's definitely a minimum visually. But then there's 2 things it asks for. It's where is the minimum, and there, so the question, it will always ask where it is, and where is the x value. So at x equals 3, and then what is the minimum? The minimum is y equals 1. So notice in the boxes there, it asks for all 3 pieces of information, like whether it's a min or a max. Let me just slip this in here. So the function has a relative minimum, and then for whatever reason it wants the y value first. So minimum of 1 at x equals 3.
Okay.
And the order, the order is important here for that. It's kind of like I live on a house on a street. Well, which house you got to give the number to? So you got to give the street number, street and the number so you can find it. Yeah. Hopefully the next one is slightly more interesting. It is. Okay. All right. Now this is going to get much more unclear because the graph they're giving you in question 6 is the derivative. So the rules are different when you have a derivative. Okay. If this were just the original function, you'd be like, hey, there's a maximum there. I get it. I completely understand. When it's the derivative, it's not that. That's not the way it goes. So there are 2 critical points. So critical points, you're used to critical points being at a min or a max. Like when we looked at this problem here, this was a critical point, and this is a critical point. A min, a max, or a min, those are the critical points. That's only true though if you're looking at the original function. When you're looking at the derivative, it's where the derivative equals 0, where it crosses or touches the x-axis. So that's why I put dots there. So your critical points are at -7 and -1.
Okay.
And that's where you're going to see some. That's where we're going to have some information. So unfortunately, we do have to actually do one of these sign charts. So there's at -7 and at -1. These are the critical points. And I mentioned in an earlier problem, when you're looking at the derivative, it's increasing. Let me go back and show you where that is. It's increasing when it's above the x-axis.
Mhm.
It's decreasing when it's below the x-axis. So there's two sets of rules, whether you're looking at the original or the derivative. So this function we're looking at here is increasing between -7 and -1. It's increasing. We use the plus symbol to indicate increasing. It's decreasing over here to the left because it's
Mhm.
below the x-axis. It's decreasing over to the right because it's below the x-axis. Now, if you're in a traditional class, they would really emphasize the following, that if it goes from minus to plus, this is considered a min. And from plus to minus is considered a max.
Okay.
So you have right here at -7, do you see how it goes from minus to plus
Mhm.
on your sign chart? So that's a min. And then from plus to minus, that's a max. So we can now answer the questions over here on the right. So let me grab just darn it. All right, let me grab the snip here of this. So this one has both is the point. And let me snip that in here. So it has a min at 7, but we don't know what the actual min is. We need more information. We can just say that there is a minimum.
Okay.
And then there's a max at -1. And that all comes from this sign chart here and this understanding of these rules off to the left here.
Okay. Okay.
All right. Okay, so we can go to 7 now. 7. Okay. So like a 7 is probably easier than 6 because when you're given the original function, you just want to make a graph of it, and that will hopefully answer most of the questions here. So let me go grab a graph of this, and we can look at it together here. Okay, so I feel like I'm missing something. Let me just check one more thing here.
Mhm.
Okay. All right, so this is a graph of the original function. And you can see it's got a vertical asymptote at 0. Okay. We're looking for places where there's either like a peak or a valley, either one of these or one of these. I don't see that in this graph.
Mhm.
Like this actually has a horizontal asymptote at wait a second. Why are they different? Oh, because they got different values. So this on the left here increases forever, and this one on the right it's also increasing forever because they're both going up and to the right. This one's much slower. This one's obviously much faster on the left.
Mhm.
So like we're not seeing the nice like some sort of a peak or valley that we're used to seeing. So this one does not have any relative extrema.
Okay.
And that's because there's no place where it has this peak or valley.
Okay. Okay, so that's D.
Yes.
Okay.
All right, so we're going on to the next one here. Use the derivative to find the vertex of a parabola. So this minus x squared tells you that it's some sort of parabola that opens down. You would have learned that in a previous class. And the vertex is where the derivative is equal to 0. Okay, now we could just graph it, but this one's fast enough. We might as well just take a derivative. So you set -2x plus 4. That's your derivative. 2 times -1, 4 times x just 4. That's your derivative. You set that equal to 0. Minus 2x equals -4. So x equals 2. Now that's just the x coordinate of the vertex. And when you were learning like college algebra, or you had a algebra 2 pre-calculus class, you would have taken that value and plugged it back in to the original function to find the y value. And that's all we do here. You just put 2 in for x minus 2 squared plus 4 times 2 plus 5. So you square before you multiply, -4 plus 8 plus 5, and that is 9. But we can check that with a graph. And I always like to double check these, especially when they count for something more than just a homework grade. So let me just check that here. And the vertex, I'll snip that in. You can see that the vertex occurs here at 2, 9.
Okay.
So they want that ordered pair, parentheses 2, comma 9.
Okay.
Okay, in the summer, the activity level of a certain type of lizard varies according to the time of day. A biologist has determined the activity level is given by the function where t is the number of hours after 12 noon. When is the activity level highest? When is it lowest? So they're trying to say that t equals 0 corresponds to 12 p.m. And just based on the answer space, so see how the answer space goes into 5:21 a.m., 6:21 a.m. So we know that like a reasonable domain for this function is like 24 hours. So from t equals 0 to t equals 24. So when I graph this on the x-axis, I'm gonna go from 0 to 24. The other way to do this is to take a derivative, set it equal to 0 and all that, but we've already sort of said, hey, let's just graph these things because they're a little bit easier to figure out. So I'm going to do that for you. And I'm going to graph with x instead of t. Just checking that I've graphed this correctly. This looks reasonable. Okay. So what I'm trying to show you here is that this is it's kind of odd that it goes negative. I guess I don't quite know that doesn't match up with the answer space, does it? 4.14. Sorry, I'm going to go back and look at that.
Yeah, okay.
Okay, it says 4:14 p.m. See, this is actually an error in the problem. So 4.14 in hours, we know that hours are 60 minutes. This would actually, there's an issue here where this 0.14, I think they meant for it to line up with 4:14 p.m. But that doesn't quite look right. And then the lowest level is at, maybe I did graph this wrong. It's not matching up. Let me go look at it one more time. 0, 0. There it is. Okay. I did fumble this badly. Okay, let me switch this up. 0 to 30. Okay, this will make more sense. Okay, here it is. I had added an extra 0, and that's what caused this glorious mistake.
What a difference.
Yeah, it's very clear now. It's like, oh, there's the peak, and there's the valley, the highs and the lows. So we're just this is your X, this is your time. So it's 5.231 hours. That's 5 hours plus you take that 0.231 and you multiply it by 60 to figure out the minutes. And that'll get you, I believe that'll get you to the, 14 minutes. So 5:14. And then
Okay.
this 18 hours later, that's full 12 plus another 6. So we'll call it 6 hours plus the 0.352 times 60. And that'll give you the other number of minutes, about 21 minutes. So 6:21 a.m. and p.m.
Interesting. Okay.
Yeah. So that looks like that's that last option there.
Oh, does that say D for you? That's interesting. I have it as C for me.
Okay.
5:14 p.m. and 6:21 a.m.
Oh no, I'm sorry. I misread it. It is C. It is
Okay.
C. I
Oh, okay.
apologize.
Yeah.
I apologize. Let's see here. Okay. Moving along here, we've got finally one we really can't graph, so we'll have to do this by hand, but it's not that bad. You have to first find the second derivative. So you first go with the first derivative. That's the power rule. So you take this 4 and multiply it by 3, 12x cubed, 4 times 3 minus 12x squared, 2 times 3 minus 9x. But wait, we got to do it again. We want the second derivative. So you just apply the same set of rules that you've learned. 3 times 12, 36
Oh,
x
that's
squared.
interesting.
Yeah. 2 times 12 minus 24x minus 9. So yeah, we've got it. We've got the second derivative. You can take an infinite number of derivatives. At some point, they sometimes repeat, but not always. Or they eventually go to 0 in some cases.
Okay, so that's the first.
Yeah, this is the first entry is
Okay.
right there.
Okay.
So now we want to find f double prime of 0. So that's 36 times 0 squared minus 24 times 0 minus 9. So that's just going to be the minus 9.
Okay.
And then f double prime of 8 is 36 times 8 squared minus 24 times 8 minus 9. I'm going to grab a calculator for that one. But where is my calculator? There it is. All right, so that is 2103. Let me just do a couple other checks here on this.
Yeah, that's what I got too.
Oh, good. Oh, good. Where is it? There it is. Oh, there, I made a mistake. I knew something was wrong. This is 6x. Yeah, that's all. The entire problem was predicated on that. So that will take this answer to 6, and it should change the last answer to 2106. But let me confirm that. Yeah, so 2106 for that last one.
Okay.
All right, I think that is it for that that question. Let's go to the next one. All right, so the next question wants the third derivative, f triple prime of x. And then, so what happens is after you go to more than 3 derivatives, you just start putting the number in parentheses. So sometimes instructors, they give sort of these, they feel like they're clever. They're like, what's the, 99th derivative of something like n factorial, or, I don't know, we'll say 99 factorial x to the 99, something like that. And the students are supposed to know how to do this, and you can figure it out a pattern, but that's why that notation is there. For us, we just need to take a first derivative and continue using our power rule. Okay, so you're just bringing that exponent down each time, multiplying, subtracting the exponent by 1, and then we do it again here. So notice the constants get knocked off each time. And so eventually, like the squareds, goes down to a 1, the cubes, the exponent keeps going down and down and down. And eventually you're not left with much in terms of a derivative. So there's your third derivative.
Okay.
But you keep going, you find that fourth derivative, which is just 48.
Did I miss the, I'm sorry, the third, no, that's why you pointed that out for.
Yep.
Okay.
Yep. The third and then the fourth.
I see. Okay. Okay. Awesome.
All right, let's take a look at the next problem here. Okay, it says to find the open intervals where the function is concave up or concave down. So the way you do this problem is, again, you do it by hand, but you can also kind of look at the graph. But if we do it by hand, you have to take 2 derivatives. So you have to take that first derivative, and then you have to take that second derivative, and then you set it equal to 0. So that doesn't leave us with much, because minus 10 is never equal to 0. If you were to look at this graph, though, it's a parabola that opens down. Okay, and concave up means that you've probably maybe heard this before, holds water. Think of like cupping your hand to hold water. Graphs either look like that or that. Those are concave up. And then down, they obviously don't hold water. They look something like this or this. So you can see that this one is always concave down. So the way you would answer this is the function is concave down on the interval minus infinity to infinity. So it's that letter A, and this is minus infinity to infinity.
And you knew that because looking at the function, it's a parabola, as opposed to the 2 little ones that you drew above that.
Well, so the parabola does not have an inflection point because it's always concave down. It's always got this kind of like down, and it just doesn't hold water. Like there's no sort of shallowing out place on it. It'll make more sense when we look at one that does have an inflection point, because this one does not. So that's the next part of this is you want to choose the one that says there is no inflection point.
Okay, I see. Okay.
Sometimes the problems are so trivial that you like can't really explain them very well.
Yeah.
But let me yeah. So actually, let's go to 14 next, then we'll come back to 13 because it'll It'll make more sense when we do this. So I'm gonna graph this one. Okay, so let me just do a quick graph of it. Please have an inflection point or two. Okay, it does. Thank goodness. All right. Yeah, so let me. All right, so here's the graph, and there's an inflection point somewhere right there, somewhere where I've made that dot, somewhere right approximately there. And if we do this in a different color, so that the red is concave down. But there's some point where it switches to concave up, where now you can see it would hold water. Is that a better visual for you? Like if you were to pull them apart?
And
Okay.
you just know that it's somewhere in the middle?
Yeah, we're gonna find it exactly, but I'm just trying
Okay.
to I'm trying to show you that, like, visually, that this one has one, whereas
Yeah.
the previous one does not.
Okay. I
Um,
gotcha.
so in terms of actually finding it, you have to take two derivatives. You have to find a first derivative, and then you have to find a second derivative, and you set that equal to 0. So you solve for x is 1. So I didn't quite have it, but it is at x equals 1. So it's closer to there is the real one.
I think your 18x should be 12x.
Yes, it should.
Okay.
Wow. I am having some problems here.
It's been a day.
Yeah. Yeah, it's unfortunately related to what I was on hold for. It's just hard to get through this. Yeah, actually I was a little closer, because it's well, no, it actually makes it worse. 9x squared minus 12x, 18x minus 12. Yeah, so it's actually x equals 2/3. It's actually even worse. It's more up here. Which I don't know if I agree with, but they don't. Well, no. I've got there's 1, so there's 2/3. Okay.
Oh, better.
Now it looks,
Okay.
now like, why does it look wrong? I don't know. Desmos doesn't put one. I don't know why they don't always put a 1 in. I don't like
Yeah.
seeing these. You have to zoom in further to get it. So that's really part. Oh no, they do ask you for part A. So the critical numbers. Oh, this one's not even asking that. Okay, let me start over here. Because I thought this was another. I felt like we could really understand this, but they're not asking for any of this. So part A is asking for critical numbers. Critical numbers are where the derivative f prime of x equals 0. And you can see there's one there and one there. Okay, the critical numbers where the derivative equals are either the max or the min. So where our first derivative correctly is 9x squared minus 12x. And you set that equal to 0 to find the critical numbers. So you can factor out a 3x out of both. And you set each of those equal to 0. So x is either 0, and that was to be expected, or x is 4/3. So in terms of like how to answer it, let me snip that in. It's the letter A with a comma separated list of 0 and 4/3.
Okay.
Okay, now visually at 0, this is a max, and at 4/3, this is a min. And so we choose the option that is consistent with that. So there's an option there. Let me snip it in. It's got a relative minimum at 4/3, because we want the x value, and a relative maximum at 0.
Okay.
Okay, we'll go back to 13. This is now very disjointed. I apologize because there's a chance there to get something out
No,
of
you're
this.
good.
Just okay, suppose the graph of the function of the derivative, that f prime derivative. So you have to now like change your thinking. It's derivative rules. Like, you know, you got this standard now we're following with derivatives, and we're talking about concavity, up or down. So before we can even talk about that, the first thing it asks about are inflection points, IPs, inflection points. And so normally, if this was the original function, be like, it's over here around, it's around x equals 1 is the inflection point. But it doesn't work that way when you're looking at the derivative. You're looking at where at the peaks and the valleys for inflection points when you're looking at the derivative. So there's inflection point at -3 and +5.
Right.
And that's because you're
Okay.
looking at the derivative. Okay, so now to figure out where it's concave up, when you're looking at the derivative, this is always confusing. It's where the derivative is going up and to the right. So in this region, it's going up and to the right. So that's concave up. So it's concave up there, and then this black over here because it's going up and to the right. So from -∞ to -3, comma 5, comma infinity. And then concave down, the rules are, again, it's kind of unclear, but it's now where it's going down and to the right. So from -3 to 5.
All right, let me just check that. Okay.
All right. Let me just check one thing here. I don't know. I just don't have a good feeling about this. Maybe, I don't know why I'm. Suppose. Okay, yeah, that is right. Okay.
Okay.
Okay, so we're back to 15. Is that right?
Yeah.
All right, find the point of diminishing returns x comma y for the function r of x, where r of x represents the revenue in thousands of dollars, and x represents the amount of time spent on advertising. So the diminishing returns is referring to probably a peak. Okay.
Okay.
This gives you your domain on this function. So when I go and graph it, I'm just gonna limit it to that window. So let me go do that, get that graph for us. Okay. Minus x cubed plus the 63x squared plus 1150x minus 500. Is that right? That's right.
It should be. It sounds right.
It doesn't have a peak or a valley, which is odd. Let me snip the graph in so you can see it as well. It does appear to have an inflection point. I mean, I suppose that's what it could be referring to. Like it's sort of increasing, and then there's this place where I don't know, it kind of looks like it bends back. If I overdo it, it's like that, and then it kind of looks like that at some point. So let me do a couple things here.
Sure.
Yeah, so they go second derivative on this one. So we have to do that by hand because the computer won't do that for us. So we're going to leave the 9/16 on the outside. It's minus 3x squared. That's your first
Just
derivative.
curious how you got to that.
The diminishing returns.
Yeah.
I just looked up a quick definition on it, and it says it's the second derivative.
Oh, I gotcha.
Because
Okay.
I mean, that's kind of an econ thing. That's probably, I mean, it probably knew that, but these questions are made and then forgotten. So you kind of go back and figure out like, what is it that they're actually asking for? So the second derivative is this bottom line here, and that's what you set equal to 0. So when you solve for that, it looks like it's 21, which would be more over here. I don't know. I don't even know if you can discern that from the graph, but maybe that is where it kind of flips. Maybe it's up. I don't know. But it does end up being x equals 21. But since they want an ordered pair, you have to put 21 back into the original function. So I'm not surprised that x value is nice, but the y value will probably need to be rounded. Yeah, it says that. So I'm going to put that into the original function and see what we come up with.
Mm-hmm.
All right, so we got 23,721.8. Probably had to check that, double check that.
That's
but
insane.
I think it's good here. Minus x cubes. Yeah. Actually, I can do that on the graph too. Why didn't I do that first? Okay, 23,721.8. Yeah, there you go.
Sorry, I'm laughing with you, not at you.
No, I know.
That's like my literal struggle every day.
No,
I'm like,
I'm hilarious. If I could make math fun, I'd have even more customers. But sometimes there's things that you just can't do to make it fun. But that does look okay.
Okay, great.
Can we just keep going here? We got 2 questions left.
Yeah, I'm good if you're good. Yeah.
Yeah, I didn't really want to stop.
Cool.
Okay, complete parts. Okay, increasing, decreasing. All right. So for the next problem here, you have to do everything. Everything meaning concave up, concave down, increasing and decreasing. So let me just graph it and see if I can see what that does for us. Ooh, really? Okay. See, if this were a homework assignment, like a traditional homework assignment, you can discern so much from the graph. You almost don't even bother to wonder if it's right. But in this case, do you see how it's going down forever?
Mm-hmm.
That means it's decreasing everywhere.
Okay, that makes sense.
Like it's
What
going,
throws me, yeah, what throws me off is that left side of it. But it's not going up and to the right.
yeah, it's going down and to the right, and then it's going down and to the right.
Yeah.
So
Okay.
like another way to think of it, if you're from a colder climate, it's like, are you excited to ski or sled down it, or or if you're increasing is like a hike, do you like a challenging hike up and to the right? So this is increasing never, but decreasing everywhere. Now we can confirm that by the first derivative. So the first derivative is minus 9x squared plus 6x minus 1. And this apparently never equals 0, which is why it's decreasing everywhere. This is always negative. And a graph of that, just to kind of illustrate what I'm talking about, minus 9x squared plus 6x minus 1. It only ever touches the axis. So it actually touches right there, 1 point, but it never crosses. So it's always negative. Now we got to be careful here. There is a critical point there. So it's not that it's decreasing everywhere. It's decreasing from minus infinity, and this is 1/3 to 1/3, comma 1/3 to infinity. So it does not include that place where it kind of looks like it switches.
Okay, and to be clear, for part A, we're choosing C.
Yes.
Okay.
With this interval.
Okay. Yeah. Okay.
Okay, so moving on to the next part where it says determine any relative extrema. So in the previous problems, we talked about how you're looking for like a peak or a valley.
Right.
And we just don't have that here. Like it goes down and then it just keeps going down. So this one has no relative extrema.
Okay.
The next one asks about concavity, but we're actually going to do the inflection point first. So the inflection point is where the second derivative equals 0. So the second derivative, I'll move this down, but the second derivative is from the first derivative, from that minus 9x squared plus 6x minus 1. So minus 18x plus 6, you set that equal to 0. Let me grab that, just move it down. Okay, so x ends up equaling 1/3 again. Okay, and we see that from the graph. Like the graph shows us there at 1/3. It looks like it's actually changing from concave up, like holding water on the left to now it's no longer holding water on the right. So that is your inflection point. You do need an ordered pair though. So to find the y value, you have to go back to the original function. You have to go back to that minus 3x cubed plus 3x squared minus x minus 3. So I'm going to put that into a calculator here and hopefully entered incorrectly. Times x squared minus x minus 3. And I think it wants it as a fraction, so got to make sure we count for that. So it ends up being minus 28 over 9. Minus x minus 3. Okay, so that's the inflection point. Now we can go back and do concavity. If you look at the graph again, it's concave up from minus infinity to that inflection point, which is at 1/3. So concave up from minus infinity to 1/3, concave down from 1/3 to infinity. So like letter C, it looks like.
Okay.
And then last part is to choose the graph. Maybe it's, yeah, graph C.
Yes.
No, I'm sorry, graph D, not C. D is the correct one.
D as in dog.
Yes.
Okay. Just for my sanity, let's go over the answers again. Part A is answer C with negative infinity to 1/3.
Yes, right here. Yes.
Okay. And then 1/3 to infinity.
Yes.
Okay. And then determine any relative extrema. Still on part A is letter D because there's none.
Yes.
Part B is answer C with negative infinity 1/3 and 1/3 infinity. Okay. And then the second part of that is answer A 1/3 comma negative 28/9.
Yes.
Okay. Okay. And then part C is answer D.
Yes.
Okay.
Yeah.
Okay. Cool.
Yeah.
That's not fair. There's like 5 questions in one question.
Yeah. Well,
Okay.
that's a different service that I offer. Just trying to work with teachers to understand that.
Huh.
Okay. So the next problem here, it's a sketch the graph of a function with all of the following properties. So we're gonna do this by process of elimination.
Okay.
And rather than like learn how to do this, students really fear when they have to sketch a graph. They're actually very straightforward. They're hard to grade, so that's why I think teachers don't do this. But we'll go through them one by one and we'll figure out which one we can eliminate. So letter A says continuous and differentiable everywhere except x equals -1, where it has a vertical asymptote. So when we look at these 4 graphs, there's a vertical asymptote at -1, -1, -1, and then at -2. So that one's out.
Okay.
All right. F prime of x is less than 0 everywhere it is defined. So that means it's always going down and to the right. When the derivative is negative, that means it's going down and to the right. There's only one graph where it's always going down and to the right.
Wait, really?
Yeah.
It's not, wait, it's not, it couldn't be B?
B is going up and to the right and then up and to the right. And
we can okay, yeah.
We can confirm out the rest of it. So we'll do that. C doesn't help us. The horizontal asymptote y equals -1. They all have that. The next one is the second derivative is less than 0. So it's concave down. It's got to be concave down from -infinity to -1. This one is concave up. Do you agree that? So that one's out. This one is also concave up. So that one's out.
Okay.
This one is concave down. And then the other stuff will be satisfied.
Ooh. Okay.